lost my checking。顾宇、赵佳琪、崔家园、陆一凡、杨如歌、李宗浩、Risky、张娜、丁、Maxine、丁。Okay. Okay. This is our the final class, and the first thing I would introduce the channel modeling on the multipath, and at the end of this course, I would talk to you about the final assignment of the presentations like that. So the first thing is the multipath. So for this course, this time, we wanted to deal with some in the multipath modeling on multipath in some very simple scenarios, and just it includes the feeding, and also in the multipath scenarios there may be some movable or mobile receivers, and they're gonna lay there is some Doppler shift or Doppler effect gonna occur. So the first thing is what we want to do is we should remember in the simulation, we should remember the geometry of the propagation scenario, because it's gonna affect the signs of the Doppler effect. All right, when the mobile receiver moves towards to the base station or moves opposite to the base station, the Doppler effect can be different. So, and also the same thing is the direction of the mobile receiver gonna affects the fading rate. All right, so especially when the Doppler effect occurs. And so the first thing is we have some assumptions. For example, if we have a receiver, so here is a base station, and another side is a mobile receiver. So the mobile receiver can move around this direction, almost this direction, and this direction, right? It has many different directions it has. So here for this class, we just assume the mobile receiver moves along a straight line. Straight line or straight route, okay. And so when we want to take sampling on the signals, so for example, it moves towards the base station, and our sampling can be in the time domain and can also be in the distance domain. All right, so the sampling can be in time domain and can also be in distance domain. So, for example, we assume it moves along a straight line and it has a constant speed. Okay, so it's we assume its speed is v. Okay, the capital V is the speed of the mobile receiver, and then moves along this direction. So we take the sampling, for example, the incremental in the distance domain is delta x, and in time domain is sampling incremental as delta t. Okay, so both can be related to delta t times the velocity, the moment velocity v. Alright, so the time domain and the distance can be connected, or it can be transferred to each other by the speed, the constant speed. So in the multipath propagation channel, the transmitted signal arrives at the receiver through, for example, several echoes, and due to maybe the diffraction or maybe the scattering and also the line of sight path. Alright, so this gonna be sometimes maybe due to the reflections by the walls or by the floor or by the roof or by the building surface or by the trees, something like that one. And so all these things should be considered in our scenario, and so we're gonna concentrate on that later. So sometimes, for example, if for the mobile communications, we really set our mobile receivers maybe surrounded by many obstacles, right? Especially in a city scenario or in the urban scenario or suburban sometimes maybe, and so there should be many multipath components from all around the surroundings, right? So, but if for the for example by the millimeter waves or the terahertz waves, we would use the much more directional antennas. So the line of sight channel gonna be employed. So the multipath components gonna be reduced, right? Because of the directional of our antennas. But the especially for the mobile communications, the base station is going to be fixed, right? So only the mobile receivers, the cell phone, or sometimes in the intelligent cars, and it's going to be moved over the trains, all right? They're going to move. So the droplet effect, it cannot be avoided. So this is the things that we want to confirm first. And the second thing is, if we wanted to express the expression of the channels, as we previously mentioned, first we approximate one channel as a line or a ray, all right? As a ray for the sometimes maybe ray tracing using in the okay. So we can assume the first thing, we assume the signal or the channel is unmodulated. Okay, unmodulated. So for the simplification, so if it is modulated, then we need to add the modulation, and the expression can be much more complicated. So now the complex form of the signal can be, as we previously introduced, it has an amplitude, all right? So, and also the exponential part, the phase part, psi. So J times the frequency and minus the propagation constant plus the initial phase, all right, if I note. And so in the this is the central frequency of the carrier frequency, all right, the carrier, and k node is the propagation constant, and phi node is the initial phase. All right. So in the real part, its real part is a node times cosine omega node t minus k node theta plus phi node. All right. So this is this part. So for the detection, actually, especially in very high frequency carrier frequencies, what we really do is we do the down conversion. All right, for the detection. So after a low pass equivalent representation, it can be represented as carrier part going to be filtered out. So by maybe a multiplexing for the down conversion, so it becomes a node cosine minus k node theta plus phi node. Okay, so we only have this part. So this one becomes a node exponential minus j k node theta plus j phi node. So this is the expression for after the down conversion. So now we have the expressions, then we can do the modeling on the multiple components. The first system is we assume we have a base station which is higher. So we have a base station. Okay. Here is the ground. And we have our base station here. And we have a mobile user or mobile receiver. As it is much lower than the base station. So we assume we have two axes. So this is the x-axis and this is the y-axis. Okay. So our mobile user moves along this direction towards the base station. With velocity v, for example. So that means it only moves, and here is the original point, 0, 0. Okay. Now this is a side bit of that. Okay, and the total distance between the mobile user or mobile receiver and the base station is 1 kilometers. So now when we assume our channel is a downlink, so the downlink means the signal comes from the base station to the mobile receiver, alright? So along this direction. But the same thing, the evolution of the expressions of the external modeling keeps the same thing for the downlink and for the uplink, alright? Because the moment is relative, alright? So when the mobile user moves towards the base station, we can also transfer it to the base station moves to the mobile user. So this is the same thing. So now, and another thing we need to consider is, we need to assume that when the mobile user moves in a short route, we assume the amplitude it received, the signal it received, is identical. So amplitude, a node, is a constant. Okay, in a short route. So we assume it's the received signal, the magnitude of the received signal is a constant, and the value that it changes is only the phase part. So the phase changes rapidly. Okay, so And another thing is for the sampling. If we wanted to obtain the details about the multi-part components, the most important thing is we should increase our sampling rate, alright? So if the sampling rate is very low, then we cannot get the full information about the multi-path effect. So the sampling rate in the distance domain, we call it maybe delta x, the smaller incremental. So it should be related to the wavelength, lambda node, and divided by a constant f. So f can be should be sometimes larger than 10, and so this is the should be larger than 10, okay, and sometimes larger than 10. So if you want to get the full information about that, you can increase it to several tens of that or to 100. So it depends on you. But so here, so then the mobile user moves, for example, along such incremental distance with delta x. Okay. So that means the initial point x 0, the distance is 0, right, in the x-axis, and at another sampling point, the distance becomes x node, right? So that means x in the second, it becomes 2 times x node, and xn, it equals n times delta x. All right. So this is the it's related to the sampling interval and related to the minimum incremental, and so in the time domain, t node should be 0. All right, and the equals is related to the velocity, so it is x node, like this one, and the time domain 1 equals delta x equals x1 divided xt t divided by v. Okay, so it's the sampling incremental is delta t, so then 2 tn equals n times delta t equals xn divided by the velocity. So now, if we wanted to assume that we wanted to get, so the distance, so the first part is really related to, in the distance domain, is related to the distance between the mobile user and the base station. All right, so the distance d is related to the, for example, when the mobile user moves to here, and its distance related to d, maybe n. So, okay, so it's the distance between the mobile user and the base station. And so the 1 kilometer we assume as capital D is 1 kilometer. So D node. So at the initial point, D node equals capital D. Alright? So when it moves to the first point, the sampling point, it becomes D node to what? Minus something. So there's another assumption that we need to consider is that, so here the distance 1 kilometer is much larger than the height of the base station and the height of the mobile user. So that means all these things can be in a straight line. Okay, so that means this station, maybe we can plot it in here. They are in the same line according maybe always along the x-axis. So that means d can be d minus delta x. All right. So yeah, straight line along the x-axis. So the dn equals capital D minus n times delta x. And we come back that because we assumed it moves in a short route, so that means x, the n times delta x is always smaller than the total distance, capital D. So this is a short route for this one. So now what we can do, we come back to the expressions for this part. Okay, so that is related to the distance between the here. Theta is related to the distance between the transmitter and the receiver. Okay, so theta can be changed to d n, like this one, can be replaced by dn. So that means now, so for example, if this one is r theta or rd, for example, so the rs can be expressed as now is rn equals a node times exponential minus j k node times dn plus j phi node. Okay, so it can be expressed as a node exponential minus j k node capital D minus n times delta x, right, plus j phi node, like this. So now we have two constant terms. The first constant term is related to the capital D, right? And another constant term is initial phase. So the varying part is only this part. So n times delta x equals v times t, right? So n is related to the number 1, 2, 3, 4, or something like that. So this term can be expressed as a node exponential point minus j k node d plus j by node minus j k node v t. So this is a constant term, and this is the term related to the moment of the users, the mobile users. So now so now we're gonna take an example for that. So we come back to this plot. Maybe I can plot it. Okay, so a straight line. So the base station, and this is the mobile user. So the distance d is 1 kilometer, and the frequency f node, the center frequency, is 2 gigahertz, for example. And so the corresponding wavelength lambda node is how much? 1.5 meter. 1.5 meter. And the velocity v, it moves this direction. Equals 10 meters per second. And so now we set our sampling number. So we take 100 sampling points. 100 sampling points. So the 100 sampling points, that means n equals 100, right? So the delta x, the sampling interval in distance domain, is related to the wavelength divided by a capital F, right? So the capital F is a number, so maybe here we chose it 16, maybe lambda node divided by 1.5 meter. It is around 0.009375 meters. So it is a very small interval, right? It's around 9.375 millimeters. So moves in a very small steps, right? Small steps. And so now the phase part, it gonna varies with respect to the distance, the travel distance. So the first thing is delta x is 100. Delta x is this term. So if we have 100 times delta x, we take 100 sampling points. So that means the mobile user gonna moves along a distance, over a distance around 100. So that's r. That's d 100. Equals this one. Equals 0.9375 meter. Alright, it's much smaller than the total distance, capital D, 100 kilometer, 1 kilometer. So that means it is a small route. Alright, so its amplitude A node can be regarded as a constant. A node is around a constant. Okay, so that means if we wanted to plot the maybe this is the distance d, okay, and its maximum is 1 meter because it's only 0.9 meters, and as the phase or the absolute phase of the complex envelope, it moves around from 0. It's gonna move. So because it moves with a constant speed, so that means the phase part gonna moves with a constant slope, something like that. After a wrap, okay, this is after unwrap. It's before the unwrap, it's gonna move something like so almost maybe to here is it's around the 1 pi, okay, and minus pi. It oscillates between 1 pi and minus 1 pi. All right, so moves like this one. Moves along this direction and then the same slope. Awesome. The same between that one and moves back to minus pi. Like this one, right? Like something. This is without a wrap. Okay. So this is the and if you want to take that wrap, there is a function in MATLAB, right? So and we're gonna take this one and do that directly. So this is the moment, the phase part, and if we wanted to say how the Doppler effect evolves, so we're going to come back to this part. Okay, to this part. So we get n times this part. So the Rn can be expressed as n node times exponential minus. Okay, here we have it in here. So this term should be a plus, I think. Yeah, should be plus to minus, and we get a plus. So now, if for the convenience, we just get rid of, because we just wanted to see the Doppler effect, so we neglect these two parts. So we get the expressions for this part again, only this part. So we get the expressions for the t. So none varies with respect to t. All right. So a node exp times J node Vt. Okay. J node Vt. So we only consider this term. And because k node equals to pi over lambda node, alright? So it is a node exponential j to pi over lambda times v times t. So like this one. And we rewrite it a node exponential j times 2 pi times v over lambda times t. Okay, and we can name this term to be fd equals v over lambda. So fd is the Doppler frequency. So it's the Doppler frequency or Doppler effect. Sheet. So the variation due to the Doppler effect, and if we wanna come back, let our previous frequency come back, the carrier frequency come back, so it becomes this one is 2 pi fd times capital T. Okay, and if we add the carrier frequency, so with the RF signal, the RT becomes a node, exp the j times omega node t. Omega node equals 2 pi f node, alright? 2 pi f node plus fd times t. So this is a standard expression for the signal or the electromagnetic wave due to the presence of the Doppler shift. So now when we come back to the the face part. And when we wanted to see, maybe sometimes now when we see this one, so it is it varies with respect to time, and also it has a constant FD, all right, added to it. So due to the presence of the envelope, the Doppler effect, it's gonna change the phase part of the variation of the phase evolution, for like this one. So here, if we see the phase part, so we come back to the phase equation. Okay, so when we wanted to see the phase part, we can see that this distance n delta x, the distance is most closer to the base station. All right, so so that means when the mobile user moves towards the base station, that means its phase part, due to the distance between both sides, should it increase or decrease? The distance moves closer, the distance should be increase or decrease? Should be decrease, right? So, but why in here we plotted it moves positively? So because we multiplied, so the phase change. We multiplied a minus sign to it, so it becomes a positive. So actually it moves downward, okay? And so the phase change moves maybe from positive to negative, like this one, for example. So that means here we assume that our base station and our mobile station and our base station, first we assume that the distance between them is much longer, it's much higher than their height. All right, so we can assume the moves the mobile user moves along straight line and towards to the base station. So along this direction. Many times that maybe our mobile user moves maybe along this direction. Sorry, I think I make something let's research. So sometimes maybe the base station actually it has a height, base station like that one, and our mobile user still along this direction, and both has an angle alpha. An angle alpha. So that means the Doppler shift is going to be changed, all right? So, and if speed is constant always so if the base station is on the same line, in the same line with the mobile user, so that means the Doppler shift is to be a maximum, all right? Maximum. So this is F max. And if the base station has a distance, maybe it's a height, okay, and so they have an angle alpha, so that means the Doppler shift should becomes smaller, right? Because the relative moment between the mobile user and the base station becomes smaller, becomes lower, for example. So that means this part should have FD related to FD is equals F max times a cosine alpha. So the times cosine alpha. So this is the FD. If the mobile user and the base station is not in a line, so like this one. This is definitely it usually commonly happens, right? So because we cannot always move towards the base station for the mobile user, we can move around or any directions we want to choose. So the Doppler effect shift is going to be modified by the angle between your moving direction and the direction and the line between the mobile user and the base station. So when we come back to the phase evolution, so for example, if this line is for alpha equals, so here for the maximum MABS alpha equals 0 degree, something like that. So if there is angle alpha, and alpha is not 0, it's larger than 0, it becomes this one. So alpha, the absolute value of alpha is larger than 0 degree. So its slope becomes smaller. And when, for example, our mobile user moves to this direction, there is a 90 degree, right? So how the Doppler shift is going to be? They are parallel. The Doppler shift is going to be 0, right? There is no relative movement between both sides, alright? So there is no relative Doppler effect. So at this point, just this point, because alpha equals 90 degree, so cosine alpha equals 0, so Doppler shift equals 0 here. So that means the slope is 0, it becomes straight line. This one. So this is for the Doppler effect. Now, if we have we wanted to transfer it to the for example, we wanted to get the distance due to the Doppler effect, the moment in the distance domain. So we named a delta L. So it is also related to here delta L. So previously we assumed that our sapling interval delta x equals lambda over f. Alright. So now because inside the conditions, its moment we should consider its moment towards the base station. So here there is a shadow on that, right? So it becomes lambda over f times cosine alpha also. So the shadow onto it. I like this one. So that's again because x when alpha equals 90 degree. So there would be no sapling point, or there would be no moment, alright, towards the base station. So that means delta L equals 0, and the Doppler shift becomes 0 also. So this is the expression for this part, and also the same thing as when okay. we're gonna continue after a short break. Now we replot it, and this is R, and this is the origin point. So this is 101 kilometers. And so we assume that the delta L equals lambda f times cosine alpha, right? So the related phase change due to this part is delta phi equals minus 2 pi over lambda times delta L. Okay, and that equals 2 pi over f times cosine alpha. So now when alpha is smaller than 90 degrees. Oh, sorry, let me see. It should be 90. Okay. So when alpha is smaller than 90 degrees, so delta phi is negative. Delta L equals lambda f cosine alpha. Alpha is positive. Phi is positive. Delta phi. Okay. So delta phi should be a positive. Should be larger than 0 because delta phi. Should be smaller than 0, yeah. And if it is equals 90 degree, delta phi equals 0, alright? So alpha equals larger than 90 degree, so it becomes a positive delta phi, larger than 0 degree. Yeah. So, okay, if when we check, for example, when alpha varies, so when we observe the, for example, if we have a spectrum analyzer, so when we take after the conversion, okay, so we do not have the information about the carrier frequency, so we can only observe the spectrum moment due to the Doppler effect. So this is 0, and so if alpha equals 90 degree, so that means there is no shift. So we're gonna observe the from the front panel of the spectrum analyzer. So the moves here. So this is 0. There is no Doppler shift. However, if the alpha is smaller than 90 degree, so the wave is gonna move to this side. So the spectrum, there is a shift. So this is alpha delta phi smaller than 0. And if alpha is larger than 90 degrees, so it moves to this side. So something like this part. So delta phi is larger than 0. This is a front panel from spectrum analyzer. So this is for this part, and then this is just for example, we have just a line of sight channel, right? So if we have maybe two we have one extra multipath components. For example, if our base station at the same direction, so this is x-axis, this is the y-axis, and the base station at this side. Okay, Now, base station at this side, and not here. It's not axis. So here is the y-axis, 0, 0, and our mobile user located here. Okay, so and here is maybe a tall building. So the first line is a straight line. The first ray is a straight line, the line outside. Okay, and the second is the reflection by the building. All right. So we have two rays. The first is the line side, another is the non-line outside. And here we assume the reflection, the reflectivity due to the building. We assume for simplification, we assume it equals 1. That's amplitude. The reflection is total reflection. Okay. And due to the reflections, there is a phase change. All right. So it's 190 degrees phase change. So it becomes -1. Okay, now the first thing is, now here is the 0, 0, and the distance between the base station, the lateral distance between the base station and the mobile user here. So it's the capital D. So again, the capital D is much longer. It's much larger. The value of D is much larger than the height of the base station and the mobile user. So this is D, and we call here is this is D, and here is dr. Okay, and when the so this is the distance. However, when our mobile user moves along this direction with constant speed, capital V, so that means we let D node to represent the distance or the lateral distance between the base station and the mobile user, and we let D1 to represent the distance between the mobile user and the building. Okay, so now we set the same thing, the sampling interval in the distance domain is delta x, and so the same thing, x node equals 0, x1 equals delta x, alright, and xn equals n times delta x. So then our D node, the distance between the mobile user and the base station, D node 0 should equals how much? Equal how much? Equals capital D, alright? Because the lateral distance is much longer than height, so we can assume they are always in the x-axis. So that means D node 1 equals D plus, because the mobile user moves away the base station, alright? So equals capital D plus delta x, and the D node n equals capital D plus n times delta x. Then when we come back to the distance between the distance between the mobile user and should be the mobile user through the building to the base station. This distance, I write it wrong. So the distance between the mobile user through the building to the base station, so this line, this distance. So that means the distance D node equals how much? Should equals the distance D node, alright? 0. The distance from the mobile user to the base station, this road, alright? It equals this road. And the times plus, sorry. This road and plus this road, right? The length. Alright? So the mobile user through the building to the base station. So it equals this part times plus this part, right? So this part is roughly equals to this part, is D node. And this part plus this part. So it roughly equals dr. So it times 2 times dr. Am I clear? So now when it moves to so D1 1 it equals now D node 1. Alright? For example, it moves to here, so it becomes D node 1 plus 2 times because it moves delta t, so dr minus delta t, because it moves towards to the building, so that means the distance between the mobile user and the building becomes shorter, right? So minus delta x, and 2 times because there are 2 roads. And this road becomes longer because it moves away from the base station. So the one node is d plus delta x times 2 dr minus 2 delta x. So it becomes d plus 2 dr minus delta x. And also the same thing as for example, d1 2, it equals d plus 2 dx minus 2 dr plus 2 dr minus 2 delta x. So it equals d plus 2 dr minus 2 delta x. So now we get expressions for the d1n. It equals d plus 2 dr minus 2 minus n times delta x. Alright, this equation. So now we get the distance between the mobile user and the base station by 2 roads, right? The first road is line of sight, another road is non-line of sight. So we can get the expressions for the for the complex envelope, right? So for the these 2 features, the first one is R node, so it equals the exponential point part of -1 j k node d for example Rn, for example d node n. All right, and another term is e minus j k node d1n. Okay, and we should add them together, right? So because we have 2 rows and we have 2 rays, and we add them together, maybe we can some interference happens. So here is plus or minus. here. You see the true here. So this one is plus or minus. As we said here, the first thing is straight line here, right? The second line is the second ray is comes to here and reflected by the building, and we set the envelope. The reflectivity is 1, and after a 190 degrees phase change, it becomes -1. So after the reflection, it becomes minus, right? So a minus because actually there should be a node here. There should be a node here, right? So and there because the reflectivity is 1, so it is a node here also. And for the convenience, we do not consider we set a node equals 1, and we neglect it. So it becomes such an equation. So now if you have maybe some other rays, you can add them always. So add maybe other terms, right? As we add all of these terms together, you can get the total envelope of this of the final received signal. Just the envelope, okay? Because we do not add the RF signal, so we do not consider the carrier frequency part. We just get rid of it for the analysis. So now we get the delta x equals n times delta x equals v times t. All right, so we get this one part to v times t and d plus d. Okay, and this term becomes this one is minus v times t. Okay, and so we can rewrite this part. So change the different to different page and R. Now, with respect to t, it becomes e minus j 2 pi over lambda node d node t minus e minus j 2 pi lambda node times d1 t. So compose e minus j 2 pi lambda node times capital D plus vt and minus j 2 pi over lambda node capital D plus 2 d r minus delta x, all right, n times delta x minus vt. So we assume initially the distance between this one equals the distance between this one. So dr equals capital D. Assume the mobile user stands in the center between the station and the building. So we can set this one is 2 dr. So dr equals D. Okay. Now it becomes node d minus vt minus e minus j to the node 3d minus vt. Okay. So now we get expressions for this one, and when we get, because for the amplitude or for the absolute value of the amplitude, that means we can get rid of the constant part of it. So the RT gets rid of the constant part. Get rid of constant part. So That means it becomes minus j 2 pi lambda node plus Vt minus e j 2 pi lambda node times times Vt. Okay, yes, times Vt again. So it becomes am I correct? Oh, sorry. I think I write something wrong. This is positive, so this one is negative. Okay? This one is positive here, so this is positive. This is negative. So it becomes E minus J 2 pi V over lambda node equals the Doppler shift, alright? So Fd times T minus E J 2 pi Fd times T again. So now we have the expressions for this one. So it equals exponential alpha minus exponential beta equals an expression as 2 times j. Okay, same. We assume 8 to be this part as minus 2 pi fdt minus this term 2 pi fdt times exponential of j times minus 2 pi fdt plus 2 pi fdt. So this is an expression for the E minus J, EJ, for example, minus EJB equals to J sin A minus B times E exponential J, A plus B. This is an expression for that. So now we get this term, and we get this term. So that means this term minus plus this term, it becomes 0, right? So this term equals 1. So we get the expressions for this term. It can be expressed as finally minus 2j sin. Oh, I think I need something half. So there is a half, and half. Okay, so sin minus the same function, so I can get the minus sign out of this sinusoid calculation. So it becomes 2 pi fd times t, like this one. So that means now we have the expressions for the envelope of the envelope of the fissure. Okay, and it moves with, it varies with period related to the Doppler shift, the envelope, all right? So and its magnitude RT can be equals magnitude RT can be relative to 2 times sin 2 pi fd times t. So this one. So now if we wanted to plot the evolution of the phasor. I would not want to plot it by myself, but I can show you that. So now due to this part, this is related to the envelope. Alright, so that means it determines the evolution of the signal along this line. Okay, this one. So when we zoom in, for example, this small part, when we zoom in this small part, it becomes this figure. So here we zoom in. So except the envelope, there is many small oscillations, right? This oscillation is related to the signal, our carrier frequency, related to that node. So when we look at this one, this looks like we have a carrier frequency and it is modulated by a signal, right? So for example, we have F node maybe as 100 gigahertz, and we have a modulation signal as around 10 gigahertz, maybe 1 gigahertz. So so this one is much faster, where oscillates much faster than the modulation signal. So this is the oscillations inside of the envelope, and here is the envelope is related to the modulation signal or the Doppler shift. So it varies like this one. So it relates to the zero because due to the interference, because we assumed the reflection is reflectivity, the amplitude of the reflectivity is 1, alright? Actually, magnitude R is much smaller than 1, alright? So maybe it's around 0.1. So when we add them together, so this term would never be 0, alright? The minimum of it should be larger than that one, because the signal between the interference, here we plot plus 0.1. So the interference is a node equals 1 and 0.1. So the minimum or the null of H cannot be 0. And the maximum or the peak of it would not be 2, alright? So this is the the channel modeling for the multi-path components. So here we just take a very simple scenario. We have 2 rays and add them together. So if we have more rays, and we should consider each of them and then add them together, get the expressions for the final phasor. So this is this part, and then next is I wanted to show about the final assignment. So the final, okay, here our overall module mark is related to, where is it? Here. So I write something wrong. Sorry, do not take picture. I just want to change. This one is 30, as we demonstrated in the first class. So this is 40%. Okay, 40%. So now I would hope you can create a video presentation by maybe the PowerPoint. and take a recording on that, just video voice. And last around 15 minutes about that. And the topic selection is just any one of the topics that we have been covered during the course. Okay, and you can choose any one of that. This topic should be. I would not want it to be too wide, and of course, you cannot present more details about that. So I would hope it is more topic, and you can just focus the presentations on just that. So the video presentation is going to provide a clear and comprehensive explanation of this topic you choose, and you can give me your understanding on that, and including maybe some key concepts, theories, applications, and any relevant mathematics. So it's not just inside of our course, maybe it's outside of it. You can just figure out some applications of that topic, and also something more. And then ensure your explanation is clear, concise, and well structured. Okay, just some basic skills for presentation. And then record it and in a format, maybe MP4 or some other formats that can be used, and send it to my email account. Okay, this is my email account, and the deadline is November 30th at 12 p.m. Okay, and make sure the video and the audio quality should be clear, and I can understand you. Okay, and also should be reflect your own understanding of the topic about that. Okay, and this is our final assignment, and then I think our course should be done. Okay, so that's it. Thank you. I would send the file to our app group, okay? And, so you do not need to take picture of it. Okay.好，我们就下课了。
是那个 PPT 不上音频。 不用不用露人吧？
啊，不用露人。
好啊，就太吓人了。
上课讲过。但是你可以往外扩音啊什么的。
昨天给那个天线高度调了，它是往里点那个没变的话，它都是会小点儿。
会小点
儿。都是会小点儿。
那它小是因什么小呢？是场景小了还是因为？
它那个高度，原来是发射机是在这块儿，接收机是在下面，它是这样一个高度，这样的。然后这回把它俩调平了，然后它是小。
啊，本来是发射机和接收机不是一个高度是吧？
对。
那我以为你是一个高度，你不是一个高度，那肯定你调成一个高度，它肯定不一样。
就是调成一个高度啊，它那个旁边。
那你还是两个不一样的高度，只是说两个同时平移这样子。就是比如说它往上移、往下移的10厘，它也往下移10厘，还是那个高度差。
高度差也变了，高
度差不要变。
高度差不要变。
对。
然后
高度可以变，高度差不要变。
哦，明白，就是完了再看。
对，要不然你高度差变了，那肯定不一样。
一开始那个发射机它默认的，那我重新测一组吧。它那个，反正就是降低它那个根据那个环境那个啥射线它都会变。但是我看它那个图它就是静态的，车啥的考虑不了。
考虑不了是吧？那可能只能我自己。
那我还看那个高度，还是直接去找新的？
直接去找新的，你看。
行吧。我说不懂。
Any question?
No, I want a picture with you.
I want what?
A picture with you. Take photo.
Take a picture with me?
Yeah.
Oh. Okay.
Yes.
So. Okay.
One, two, three. Okay, one more. One, two, three. Okay.
Thank you.
Yeah. Teacher, I want to ask something. Can I present my paper that I saw you before for this final exam?
The final exam?
Yeah. I want to present my paper.
Oh, even the file?
Yeah.
Okay. Yeah, I think so. Yeah, you can. Sure.
Okay.
And I can present on microscope antenna.
Okay, sure. You can. Yeah, I think because it should be inside of this scope. So it should be okay.
Microscope.
Thank you very much.